This lesson is about confidence intervals for means. To understand what that is, let's consider this question. Suppose we wanted to know the average of American males' weights. Well, we could weigh every American male, but that's not practical. Population is too large. So what we always do is we take a sample and we use that random sample as a representative of the population. And what we want to get here is the value of mu meaning the population average. But in order to estimate that, we're going to have to give sort of a window of values. We're going to have to make a statement that says something like mu is between this and that. The average American male weighs between this amount and that amount. Because without being able to weigh the entire population, all we can give is this window of values, also known as an interval. So our confidence interval is going to be this statement. So in order to calculate that, suppose we randomly sampled 20 American males and weighed them. Here are the results. Now it turns out this sample average shown here is 201 pounds. You could compute that yourself by just adding up all the weights and dividing by 20. And we call that X bar, or our sample average. We also call it a point estimate, because if at this point we had to say what the most likely population average would be for American male weights, the one point or one number that we could say at this moment is, well, 201. But of course, samples vary, so we don't know for sure that the population average is 201. Suppose we wanted to make this statement with what's called 90% confidence. More on that later. In order to do that, we're going to need three things. We're going to need a standard error. We're going to need something called a critical value or critical t-value, and we're going to need something called a margin of error to see just how far off our point estimate might be. Well, let's start with standard error. In order to compute what's called the standard error, we have to have a sense of how much variation in weights there is among American males. Now, if I knew the population standard deviation for American males, I would use that to compute my standard error. But suppose I didn't. Suppose all I knew about variation among American male weights was the sample standard deviation, also known as S. And suppose I knew that that were 10.4. By the way, I got that number from the 20-person sample. In order to do that, you could calculate this by hand, but more than likely you would feed all these numbers into some kind of software or calculator, and it would tell you the sample standard deviation, which I did, and it turned out to be 10.4. By the way, in a problem where the population standard deviation is not known, and we're using the sample standard deviation to compute the sample error, which I'll do in a minute, we typically call those problems sigma unknown problems, which sigma representing the population standard deviation, and that name indicating that we don't know it, and we're using the sample standard deviation as an estimate. So when that's the case, you compute standard error by doing the sample standard deviation divided by the square root of the sample size, which in this case was 20. More generally, we could say the standard error is S divided by the square root of n. And that, by the way, works out to about 2.37. What does that mean? Well, in some sense, what a standard error means is that if I were to find out that my point estimate were off from the true population average by 2.37 one way or the other, I wouldn't be surprised. In some sense, it's an expected difference that might occur between x bar, and mu. Let's move on to critical value. We're going to do a critical value using what's called a t-distribution. We're going to get a critical t-score. And if you've never heard of a t-distribution before, it's very much like a normal distribution, where we would find a critical z-value. But the t-distribution takes into account sample size. So, what I'm going to do is I'm going to use something called an inverse t function as shown. This number here, by the way, essentially is one less than the sample size. Because I had 20 people in my sample, one less than that is 19. By the way, this number is also called the degrees of freedom, and that's a very broad term that we won't delve much into here, but in short, let me say that your degrees of freedom on a problem are the number of samples minus the number of parameters you're estimating. Well, we have 20 samples and we're estimating one parameter, the American male weight. 20 minus 1 is 19. But to make it simple, that number will always be n minus 1, or sample size minus 1. Now when you put this into a calculator or into any other kind of software, what you get is 1.729. Well, let's take a minute to examine what that means. What that means is the following. In this case, I want to produce what's called a 90% confidence interval. That means I want to use a process which will give me a confidence interval that captures the population mean 90% of the time. And in order to do that, and I have to accept that there is a 10% chance that I will not capture the population mean. And this t-value is the number of standard errors that I'm allowed to be away from my point estimate in order to have a 90% efficient process. And the critical t-value is right here. Now, the way most calculators and software design the inverse t function is they want the area under the t-distribution to the left of the critical t-value that I want. And since the area to the left is 95%, which basically comes from 5 plus 90, you can see the rationale for the formula that's shown above. One way or the other, there's my critical t-value. Next, let's compute margin of error. In order to compute the margin of error, I simply have to multiply my critical value times my standard error. And that makes sense if you think about it this way. The critical value of 1.729 means that in order to have a 90% efficient process, I can be off by 1.729 standard errors. If each standard error is 2.37, then I would multiply those to get the amount that I can be off, also known as my margin of error. I'm going to round that number to 4. So let's analyze what a margin of error of 4 means. Remember my point estimate of 201? That one single number, that sample average that would represent the population, if that's all, if I had to pick a single number to represent the population average, I would pick that. Well, a margin of error of 4 means that with 90% confidence, that point estimate is within 4 of the true population mean. which indicates that the true population mean, mu, could be as much as 4 higher than that, or mu could be as far down as 4 lower than that. And these red numbers are the lower and upper limits of my confidence interval. And so finally, I can make a statement about my 90% confidence interval, that the average American male weight is somewhere between 197 and 205. And that completes the lesson.